Solving quadratic equations with complex coefficients. So if we have a quadratic equation in the form ax squared plus bx plus c equals 0, we know if a, b, and c are all real, our roots are either going to be real or complex. And if they're complex, they're going to occur in conjugate pairs. But if any of A, B, and C are complex, there's no real simple solution, and we're going to have a look at a strategy that we can use to help us solve it if they're complex. And we'll do this with an example. So we're going to have a look at x squared plus 2x plus I equals 0. Now here we have one coefficient that's complex, and if we have this, the thing we need to do is we need to complete the square. So in order to do that, let's take the I to the other side. So we'll have x squared plus 2x equals minus I. Now we can go ahead and just half the coefficient of x and square it. So half is just 1 squared, and we'll add this to the other side. So 1 squared is just 1. And now we can go ahead and complete the square. So we're going to get x plus 1 all squared equaling minus I plus 1. Now, here what we actually want to do is we want to let the thing inside our perfect square, so x plus 1, equal to alpha plus beta I. And this is going to help us equate coefficients. So let's do that. So we get alpha plus beta I all squared equals minus I plus 1. Let's expand this left-hand side. So we get alpha squared plus 2 alpha beta I squared. Whoops, it should just be I, 2 alpha beta I, plus beta squared I squared. And that equals 1 minus I. Now, I squared is minus 1. So we get alpha squared minus beta squared plus 2 alpha beta I equaling 1 minus I. And what we want to do now is equate the real parts of both sides of the equation with each other and the imaginary parts with each other. So we can get a couple of equations. We can get alpha squared minus beta squared, that's the real part on the left-hand side, has to equal to 1. And we get 2 alpha beta has to equal to minus 1. So this is equating both sides of our equations together. Now, what we want to do now is actually we want to write an expression for alpha squared plus beta squared all squared. And if we expand this out, we're going to get alpha to the 4 plus 2 alpha squared beta squared plus beta to the 4. And this will equal, we're going to use the expression alpha squared plus beta squared all squared. So this might be one you have to commit to memory. Equals alpha squared minus beta squared all squared minus plus 2 alpha beta all squared. And we can confirm it's true if we expand our right hand side, so we get alpha to the 4 minus 2 alpha squared beta squared plus beta to the 4 plus 4 alpha squared beta squared, and the minus 2 alpha squared beta squared and 4 alpha squared beta squared just equal plus 2 alpha squared beta squared, which equals the right hand side. So we know that equation holds true, and it's going to be helpful. It's going to be helpful to us to solve this equation, because now we can say that alpha squared plus beta squared all squared equals alpha squared minus beta squared, which is just 1 squared, plus 2 alpha beta, which we know is minus 1 all squared. So we get alpha squared plus beta squared all squared equals 1 plus 1, which is 2, and we can square root both sides. And we get alpha squared plus beta squared equals root 2. And what we can do here is, this was equation 1, 2, and now we've created a third equation for alpha squared plus beta squared. We can go ahead and add 1 and 3 together. So we get 2 alpha squared, and then the beta squared and the minus beta squared cancel out, and we get root 2 plus 1. Times both sides by a half, so we get alpha squared equals root 2 plus 1 all over 2, and then square root both sides, and we get alpha equals the square root of root 2 plus 1 all over 2. Should be plus or minus. This is pretty ugly, so what we might do is we'll try and rationalize the denominator. So we'll times by root 2 over root 2, and that's going to give us alpha equals plus or minus. Might be tricky to see, so let's just break it up. So we're going to say root of root 2 plus 1 times root 2. Now over root 2 times root 2 will just be 2. So it'd be plus or minus. Now we have a square root times a square root, so we can write it as one big square root, and everything inside we need to multiply together. So we've got root 2 plus 1 inside our first square root, and we've just got 2 inside our second square root, all over 2. So we get alpha equals plus or minus root 2 times root 2 is 2 root 2, and 2 times 1 is 2, and this is going to be all over 2. So we get two answers for alpha, one being the square root of 2 root 2 plus 2 on 2, and minus root 2 root 2 plus 2 all over 2. We want to go back to equation 2 and make beta the subject. So if we do that, we'll have beta equals minus 1 over 2 alpha, and we can go ahead and sub these two values of alpha into here to get two values for beta. And we can't forget, in the first place, we also let x plus 1 equal alpha plus beta r, and we're going to use that as well. So let's keep going. So subbing into beta, we need to do it twice, where beta was minus 1 on 2 alpha, and our values for alpha were the square root of 2 root 2 plus 2 all over 2, and minus square root of 2 root 2 plus 2 all over 2. And remember that we let x plus 1 equal alpha plus beta I. So this is all the info we need to keep going. And so beta, well, we need to multiply by, we can multiply minus a half by the reciprocal of alpha, because the alpha's in the denominator. So we're going to have to multiply by 2 over the square root of 2 root 2 plus 2. And beta is also going to equal minus a half times the reciprocal of our next value for alpha, which is minus 2 over the square root of 2 root 2 plus 2. So the 2's will cancel out. So we get beta equals minus 1 over the square root of 2 root 2 plus 2. It's pretty ugly to have surds in the denominator. So let's try and rationalize this. So this is going to take, we're going to have to multiply by the conjugate. So we're going to have to multiply by root of 2 root 2 minus 2 over root 2 root 2 minus 2. And since these are the same, they only differ by the negative, we'll be able to use this for our next value of beta as well. So let's go ahead. So just times the numerators just gives us minus root 2 root 2 minus 2. Denominator is the tricky part. So what's going to happen is we're going to get the square root, the big square root of 2 root 2 plus 2 times 2 root 2 minus 2. This is going to give us minus the root of 2 root 2 minus 2 over, to evaluate everything inside the root. So 2 root 2 times 2 root 2, well 2 times 2 is 4, root 2 times root 2 is 2, and 4 times 2 is 8. 2 root 2 times minus 2 is minus 4 root 2. 2 times 2 root 2 is plus 4 root 2. And 2 times minus 2 is minus 4. These are going to cancel. Then we're going to get 8 minus 4, which is 4, and root 4, which is 2. So we've successfully rationalized the denominator. So we do end up with minus 2 root 2 minus 2 over 2. And for our other value of beta, the minuses cancel and the 2's cancel. So we end up with 1 over root 2 plus 2. And we know that's just going to be root 2 minus 2 over 2. And this is the positive value. So then we get so we get two solutions for alpha and beta. So we know x plus 1 will equal, let's look at our first pair of solutions. So we've got alpha, which is root 2 plus 2 over 2 plus its matching beta. So that matching beta was when beta was negative. So let's put a negative in there. So minus that value of beta, which is root 2 minus 2 over 2i. And then we have our other answer, where x plus 1 equals the other the negative alpha. So negative root 2 plus 2 all over 2. Then our positive beta, so plus root 2 minus 2 over 2i. And finally, we just have to minus 1 from both sides of both equations. And we get x equals, so This one's equation 1, and this one's equation 2. So equation 1, we're going to get x equals root 2 plus 2 all over 2 minus 1 is our real part, minus root 2 minus 2 all over 2 multiplied by I as one solution. Then our second solution is just x equals minus root 2 plus 2 all over 2 minus 1 as our real part, plus root 2 minus 2 over 2i. And there are our two solutions to that quadratic equation.